Welcome everyone to our first to our webinar, the first fuzzy logic Autotuner. So in this webinar, what we will be covering is AI and fuzzy logic, the tuning problem, Zera's solution, edeX explained with an in-depth demo, as well as applications followed by Q&A. Now, that said, feel free everyone to use the Q&A button liberally throughout the presentation. We will be taking a look at it and we'll try to incorporate any questions that you have as we're going through the presentation. So today's speaker, myself, Abraham, as well as Dr. Talib Janabi, who's our founder with 2 patents in artificial intelligence, Dr. Elaine Marsman, who's our co-founder and senior software developer, and Mehak Gawar, who's a professional process engineer and is in business development here at Zera. So let's begin just broadly looking at artificial intelligence. So artificial intelligence is the branch of computer science that is concerned with the study and automation of intelligent behavior, such as that of animals and humans. Branches of AI include machine learning, neural networks, fuzzy logic, expert systems, language, data mining, and data warehousing, and others. What we're going to be focusing on is fuzzy logic, which is where we work in. So fuzzy logic is a decision knowledge-based system, which allows us to better mimic human-like thinking processes. And the areas of application of fuzzy logic include control and automation, prediction and forecasting, recognition, modeling of complex systems, decision-making, production planning and scheduling, diagnostics, management, language translation, and more. Now, our ability to tune the fuzzy logic parameters can be applied to any of these areas. However, what we're going to be focusing on is control and automation, because that's the area that we've actually been working on at Zera. So control applications include temperature, motor speed and stability, battery charging, distillation columns, pressure level, fluid flow, voltage, and much, much more. The reason why the first 4 are highlighted are because these are areas that we have actually worked in so far, and Mehak will be talking about that later on in the presentation. So why fuzzy logic control? It's been around for decades, and what we've seen is that generally we can have up to 35% energy savings. There have been results that have been even higher than that, up to 30% raw material savings and decreased wastage, and up to 30% less air and noise pollution. So real examples of where this has been applied in the process industry is Nippon Steel in Japan reported up to 30% savings on product wastage using fuzzy logic in a steel plant. And in terms of embedded applications, we have rice cookers, washing machines, vacuum cleaners, robot controller, and many other embedded applications. And over here in the middle, you can see the coveted fuzzy rice cooker. I was looking up an Amazon review, and someone was saying that it was the best rice he'd ever had. So here's the real question. If fuzzy logic control provides significantly superior solutions, why isn't it the industry standard? And the reason is because it's difficult to tune fuzzy logic controllers. And like all controllers, fuzzy logic controllers must be tuned separately for every application. So you can think of controller development in this workflow. So you have first data acquisitioning, then modeling, then tuning, then testing, and then validation. And basically, the problem occurs here. Okay. The reason why there's a problem is because fuzzy logic controllers use a large number of parameters, around 20 to 40 for a simple single input, single output application. Now, if you compare that to the PID, which only has 3 parameters, you can see that the PID would be much easier to tune. For more complex applications, the number of fuzzy controller parameters can easily go over 100. And in fact, we've had examples where we had over 700 parameters. So this task requires extensive experimentation and can take weeks or months. When done manually, it requires expert knowledge, and there are many hurdles to overcome. So this is a bit of a simplified picture, but the current state of the industry is that for a PID, for single input, single output systems, there is an industrial auto tuner available. But for fuzzy logic controllers, neither for single input, single output systems, nor for multivariable interactive systems do you have an auto tuner available. So Zera's solution is edeX. Xera has developed edeX, a computerized proprietary intelligent system to tune the fuzzy controller parameters automatically within minutes. edeX is a fuzzy logic controlled development environment consisting of software and hardware. edeX will program a chip with the tuned fuzzy logic control parameters as easily as conventional control methods. So edeX can be used to auto-tune both the PID and the fuzzy logic controller for both single input, single output systems, as well as for multivariable interactive systems. edeX's software is a development environment designed to be used for the entire development of control applications. So when we say we have an auto tuner, right, that's only covering one area, the tuning area, right? But this other stuff that needs to be done in the controller development is done by edeX. So we've created basically a complete package which can be used for the entire development, including an auto tuner. So our mission, what do we want to do with this? We want to protect the Earth by reducing global energy consumption and pollution through optimized control, right? What we want is for fuzzy logic controllers to obtain widespread usage, in factories, in cars, in big energy consumers, and to bring that consumption down and to bring the pollution down, to minimize our ecological footprint through optimized control. It's as simple as, not wasting. And now with edeX, this becomes possible. So now I'm going to pass it off to Dr. Janabi, who is going to, show us how the workflow would look like in developing a controller. Dr. Janabi, if you want to share your screen.
Thank you, Abraham. Welcome, everybody.
So just 1 second, folks, while we get that sorted out. If you guys have any questions about what I've said so far, please feel free to use the Q&A function and let us hear your thoughts.
Can you see my screen
Yes.
now? Okay. People in control know that although it is transparent to sometimes even the end user, but the workflow of tuning any controller is by obtaining data. You do data acquisition. I'll say why we need that. Then you do a model of the process. You tune your controller, you test it, and then you go to validation. And I'll talk about this in a minute. I'll go through this very quickly. Why do we need data acquisition? Actually, most people think that data acquisition is probably something that you have stream of data day and night. No, for controller, you don't need that. All you need is to send a disturbance to the process you want to control. Say you want to control the temperature, flow, pressure, and so on. You send a disturbance, you receive data, the response for the disturbance, and that is what is called data acquisition. So that is done within a minute or even less or a little more. So a disturbance and the process response for the disturbance, that's the data acquisition that we mean when we say data acquisition. Now we have that data on file, we create a model. And that model, of course, the better the model is, the better your tuning is. However, for fuzzy controller being intelligent, you don't need an accurate model. An approximate model is sufficient. But our Autotuner actually can get quite an accurate model for the data received. Once we have the model, we go to tune our fuzzy controller using edeX software. Now that we have the tuned fuzzy controller, we download the knowledge base or parameters to the chip on the hardware, which is our own hardware that is connected already to the process, and that's how we got the data acquisition. Maybe Alan will go through that later. Then we do the testing, and that testing is done using edeX software. You send signals, and that signals go through the process, and the fuzzy controller that's on the board will do the control. So now you've done all the testing, you go to the validation. Now, what is validation? Validation is when you take your the fuzzy controller and you put it on your own hardware or software, and then you validate it in your own environment. So that is the whole all the stages at the moment using edeX, because edeX is a development environment, and it allows the user for to have access to all the stages of data acquisition, modeling, tuning, testing, and validation. It's not one push button, although it can be at a later stage. In particular, when we go to the process industry, that can be done. It's a question of putting the software right. But also, when we go to the software, we can allow the user to have access to all these stages, so the user is happy and comforted by seeing what is happening. I think that is what I wanted to say about this workflow. I will show you now how we do the modeling and how do we the tuning. Later, Alan will show you the data acquisition. So now, although this is our new environment, our new interface for the edeX, which everybody must have seen an interface like this, is quite intuitive. However, because we are still working on it and there are some still some bugs to be cleared, I'm going to use the old interface for the modeling. For the tuning, I'll probably use the new interface. So what we have here, we have, this is the old interface. I'm not going to go through it because it's not going to be relevant. But in any case, here is the data file. And let me remove that. Here is the data file. And then this is a transfer function 111, just any transfer function, anything. Of course, for more complicated environment, you can use many other blocks. Here we have linear elements, we have mathematical elements, we have nonlinear elements, and we have discrete time blocks. So you can actually put the the right blocks that you want. In one of the applications for battery, I actually used fuzzy controller itself as a model, not just as a controller. And I used I used 3 fuzzy controllers in parallel, plus linear elements and gain, to get the right model. But in any case, that's so what I'm trying to say here is this could be as expanded as you want. So we'll look through in this here. What we have here is that these are the changes. This is the parameter, the behavior of the system, and this is our initial. The blue line is our initial model, which is 111. That's just nothing. So when we go here, so we want to go there, and we have an error criteria. And actually, we are using very simple error criteria, just error, the difference between the two. Of course, we can develop that to be more complicated kind of criteria, but even with this simple criteria, and as you can see here, I have just put maximum value of the error 0.02. It could be anything, 0.01. It could be 0.1, whatever. And the variables that I am tuning here for the model is the transfer function itself. So here are the set values. We'll go through those at a later time. So now I'm going to go through this very quickly. I'm going to just say run, and you can see it found the model very quickly. And it found a relevant model very quickly. And the model here is this kind of a transfer function. So now, having done this, I'm going to close that. I'm going to say, okay, then I came here and I put the model here, and I put the fuzzy controller here, and I am trying to tune a fuzzy controller for this kind of system. So now, when I run the initial fuzzy controller, initial means actually nothing more than just using membership functions that are very simple, 0.5 to 0.5, 0.1 to minus 0.1 to 0.1, minus 1 to 1, and the default rules are just, you know, n, z, 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 that's negative, negative, z, 0, 0, positive, positive, high, high, high. So it's really a simple default. And we are hoping that the fuzzy controller, that the tuner will find the right parameters. Now let's go to see what we are tuning here. So we are tuning here. Let's just try. First of all, we can try to tune the membership functions only, or the membership functions on the rules, or we can tune the rules, the rule weights, against membership functions. We can, depending on the complexity of the system. Now, then how do we get that right? Well, we have the step response. We have overshoot 0, maximum, or it could be something very small, maximum rise time. Those parameters, rise time, settling time, etc., depend on the kind of system that we're dealing with. So I'm choosing here 0 zeros, and this is a very simple choice of rise time and settling time. The designer can make choices, can later come and change the choices, change the tuning until until he or she get the right tuning they like. And as you can see, we're going to tune this in a very short time. You can see that kind of few seconds is what we're talking about when we say people take weeks and months to actually get this right. So as you can see here, our fuzzy control, our tuner has found nice parameters here. So we'll see what it has found, and we can look at our MFs, and you can see those MFs have changed, and we didn't tune the fuzzy rules, so that's okay. They stayed as they are. In a more complex system, we can do that. So now what we're going to do is we're going to put some, okay, before that, what I'm going to do is I'm going to see if my controller is a robust. So I tuned it for 1, meaning 100%. So for whatever the process variable is. So I'm going to go to 2. 2 means 200%. Of course, there is no such thing in real life. But just to show the robustness of the controller, and you can see, it went to 2 rather nicely and easily. If I go to 300%, what do I get? I get nice thing here. So if I go to 0.5%, that is 50%. What do I get? I get also nice response here. So now, I'll go back to 1, and what I'm going to do is I'm going to add disturbances. So I'm going to say I'm going to add disturbance of 100% and of minus 100%, minus 1 plus 1, just to see how this system is behaving. And as you can see, even though the disturbance is rather very large, still the controller was able to bring the system back to the set point nicely. So that's what we mean by what we're so now what I'm going to do as an added thing, I will tune the rules to see what we can get if we add complexity. The reason why I didn't tune the rule is because this system is simple, that we're talking about is a first order system. And so you add more nonlinearities, you add complexities unnecessarily. But I'm going to try this. I am not really sure adding the complexity will be a good thing or a bad thing. So motor tuning. So that's the same thing that we have started. And let me see if I can throw the rules as well. So let me throw the rules into the equation, and let me see where do I get with that. And as you can see, tuning the rules, the membership functions, the controller actually found another combination with the rules as well as the membership function. Now, most people who talk about fuzzy controllers and tuning fuzzy controllers, they only tune the membership function. Nobody tunes the rules, not that I know of at least. So now I'm going to do this just to show the actual power of the thing again. So I'm not going to I'm not going to go through the whole thing again. We have no time for that. But as you can see, I increased it to 100%. Let me see what I'm getting for 300%. And there you are. So it's the same thing. So that is what we're talking about. What I have done here is a tuning of rules and membership functions of a fuzzy controller that people take weeks or maybe more to do it. Thank you very much.
Sorry, we have a question here. Could you also show the plot for control effort?
Yeah,
and
sure.
also, can you explain the relevance of the ability to tune both the rules and the membership functions?
Okay, let me. This is the control effort here. So this brown-looking thing is the controller output. For that, so if I go back to 1, the 100%, oops, and I go to, so it's a similar thing. Sorry, the question was the relevance. Abraham?
Yes, so I was saying, you were mentioning before that other people who tune fuzzy logic only tune the membership functions. They do not tune the rules.
They do not tune the rules. They use they work out some sort of rules and then put them in the system. And then they tune the membership functions only. Well, that will give you some combination, but not necessarily the optimum. Obviously, the optimum will be when you put all the rules, membership functions, gains, scaling factors all together and tune them. However, I must say that you know, from our experience, we found that you do not need to tune every variable in the fuzzy controller for every system. You can select which are more relevant, or you can choose some combinations, tune them, then see which combination gives you the best response. Now we can of course automate that at a later stage. The reason why I'm saying that different combinations may not give you the same thing, like in this situation that I've just done, different combination gave you more or less the same thing, is because if your system is linear and you're adding nonlinearities to it, then you may end up with a suboptimal performance because you're just adding to the system more than it can take. So yes, you can add those nonlinearities or the rules and other membership functions. And by the way, just one thing I forgot to mention, that the membership functions here that we can give here, you know, we can use triangle, we can use trapezoidal, we can use Gaussian, we can use bell curve. So there are all kinds of combination of different types of membership functions that can be used depending on the application or the preference of the user.
So the question's also asking to see the curve for 0.5 set point with disturbance.
in here?
Yes, with disturbance.
Sure. There you are. So with this here, I've got a little bit of ripple here, but that ripple didn't seem to matter. It got me where I wanted. If I tune it a little bit longer, another minute, I probably get much better response. But I think that's enough for the demo.
There's another question about how does the FLC compare with adaptive control techniques?
It's a different thing. Adaptive techniques are mathematical algorithms. I don't want to go into the depth of technology here, but it's a completely different field. This fuzzy technology is intelligent technology. It's intelligent by nature, meaning that the actual algorithm is drawn and it depends on the fact that, you know, how does a human think? Here is how we think, and therefore we transform that into a methodology. It's the adaptive algorithm or adaptive control are mathematical, algorithms. Probably some intelligence are added to it from the outside, but not from the inside.
We have another question here as well. How can I integrate the fuzzy logic autotuner? I think he means like edeX as a complete platform, or perhaps just the autotuner portion of that. I'm not sure. So he says, how well can I integrate the fuzzy logic autotuner with DCS platforms such as Emerson Delta 5, Honeywell, Yokogawa, etc.? Can it be integrated using OPC? Or is this meant as a standalone specialized software package? Can it be integrated with PLCs such as Allen Bradley and Siemens?
Okay, at the moment, it's a standalone package, and it works with our hardware. However, it can be easily modified to be integrated if people are interested. It requires a bit of development, of course, but integrating it is not a big issue.
Okay, perfect. With that, I think we'll move on to, and the person says, thank you for the answer. So with that, I think we'll move on to Dr. Elaine Marsman to show us the rest of the workflow development.
Right, thank you, Abraham. Hello, everyone. I'm just going to share my screen here.
Yep, go ahead. By the way, thank you everyone for the questions. We really appreciate it. It does make it more engaging, and we appreciate hearing what you guys are concerned about and what you guys want to learn more about. So please keep sending the questions our way, and direct us where you want us to kind of take you in terms of your interest with what we have to offer.
Is my screen visible?
Yep, you're good to go.
Okay, great. Okay, so as Talib had shown you, he showed you basically the software portion of edeX, how you build a model based on I/O data, and how you use that model to tune a fuzzy loop to get an optimal control response. So I'd like to focus now on the downstream portion of the workflow, which is implementation on a real-time hardware platform and integration into a real application, or host application. So I'm just going to, so this picture here that you can see here is basically a close-up of the edeX hardware in the hardware system. And the heart of it is a small board here on the left, which is the fuzzy logic control board. So here on this microcontroller, we have the fuzzy logic algorithms are pre-programmed onto the board. And the edeX software, what it does is just basically programs the parameters for each application onto the flash memory of the chip. And that's done through this small USB jack, which communicates with the edeX workstation. And once it's programmed, this little board is now a ready to go fuzzy logic controller, basically. And this can be integrated into any kind of host application through this black header here, which exposes essentially the serial port, the UART of the chip. So any host application can drive the algorithm by sending a small binary message requesting the execution of the algorithm, and then the chip will return back your answer, basically. So given where's my set point, where's my process at this time, what should my control effort B. Now, as part of the development and prototyping environment, we also included these larger boards. The large board is our evaluation board, which hosts these small I/O modules, which are sort of swappable and flexible. So we support many standard, I/O signal formats, 0 to 10 volts, but binaries 0 to 10 volts, 4 to 20 milliamps, reading thermocouples and temperature sensors. We can output pulse width modulation signals, or just voltages, or the whole range of typical kind of control signals that you see in the industry. So what the user can do is use this small EVB here to very quickly and cheaply connect to their system, take measurements for data acquisition, create their model, tune the fuzzy loop, and then test it directly using our hardware without having to develop their own prototype. Of course, if you already have an existing application or prototype, let's say you have an SBC or another system where you can get I/O data already, and you can interface with your process, then you're more than welcome to just directly integrate the small controller board. So given that, I'd like to now demonstrate how we download or how we program the microcontroller unit with the fuzzy logic controller, and how we can validate that in real time. So what I have here is an example. So this is not the motor example that Talib was showing, but it's a slightly different one. So this system here has nonlinearity in it now. So we have essentially linear portion, a transfer function here, which is a pretty high steady state gain of 10. And then as well, there's a dead zone. So the control effort will have no effect on the dynamics when it's within this minus 0.3 to 0.3 range. It's quite a large, it's maybe somewhat artificial, but it'll show the power of the fuzzy controller. So this is being tuned already. And you can see here, this is the unit step response. So, excuse me, the blue is the process variable, and this brown is the control effort. And you can immediately see how nonlinear the fuzzy logic controller is. It starts off very high, very strong output to drive the process quickly to the set point, but it's intelligent enough to know that it has to break it quite dramatically before it overshoots, and so it settles nice and quickly and smoothly to your set point. So what we'd like to do now is put this fuzzy logic controller onto our chip and see how we can validate it from there. So to do that, in this other example, in this other project here, what I've done is I've taken just that fuzzy logic controller block, isolated it, but this is the same fuzzy controller. And I've used these small terminal blocks to sort of define the I/O points for this controller. So the controller takes two inputs. You tell it the set point, you measure the process variable, and it will compute your control effort or control output signal. So the idea is this small block diagram now represents our controller, and we're basically going to program that onto our chip. So the chip is currently connected, or the FLC board is now currently connected to my system to my USB cable. So if I open the relevant dialog here, I can communicate through the COM port, and this is a standalone FLC board, which we call the XCM. And when I connect to it, this basically shows you a map of what's available on the chip, how much flash memory is available, where you can store your parameters, et cetera, et cetera. So right now, this is an empty chip, basically. So what we want to do is program these controller parameters onto the chip. So I'm going to choose one of the regions of memory here, give it a small description, my FLC. This controller here was developed for a 0.1 second execution interval. So we have to tell the hardware we want to run it every 100 milliseconds. And now I program the chip. And now that the chip stored in the memory has the controller. And you can see here it's got two inputs, one output, and here are inputs and outputs and their ranges. So this is now a ready to go controller. Now, typically, if this were connected to a host application with a real system, you could actually try running the full loop and monitoring it to see how it performs. But before you do that, there's an intermediate validation step you can do where you can actually run this controller as a hardware in the loop and use the edeX software to simulate your process response and see how it behaves. So to do that, let me just disconnect here. And this other project I have here, oops. So this diagram now is the opposite of the controller diagram. It only has the process model blocks. So here's our transfer function that we had and our dead zone. So we're telling the edeX software now, I'm going to give you the control output, and you're going to compute what the process, how the process would respond. This is all in software. So if I connect to my controller board again, you see here the fuzzy logic controller is still in a non-volatile memory. And I can go to my controller testing tab and tell the edeX software that I want to do a simulated closed loop control test. So basically now the controller is running on the hardware in real time, but the process model is running on the software. And then I basically connect the two together, saying that the PV input of the controller will come from this PV block, this PV signal here in the model, and the control output from the controller will be fed into the CO terminal block here and go into our process model. So now we've connected a closed loop, and I can open this window to start the controller test. So let's start with a unit step and see how it responds. You can also, if you prefer, or if you need to, you can save all this data, this real-time data, to log file for your later analysis and graphing. So here we start, and we can see in green the controller output, and in blue the process variable response, and the black is the set point. So just like in the pure simulation case, it reaches the set point smoothly and it holds there. And again, you can see the nonlinear behavior of the controller. Very rapid output near the beginning, and then it can break the response as it requires. So let's see if we go another 100% up. And we reach now the next set point. So you can see that this controller is fairly robust, and it behaves smoothly in real time as well as in the simulation. Let's see if we can bring it back down again. So here it's going basically to its lowest possible output and letting the process decrease. And then it sees that it's approaching quite fast, so it's going to give it a small burst of control effort to break it and make it smoothly reach the set point. So this is the essence of basically a real-time validation. I mean, the next step is to actually run it on the full external system, and they can still use the edeX software to monitor it at least and change set points, et cetera, et cetera. Okay, so that's essentially really what I wanted to show today. So I think this sort of covers the entire workflow from modeling your process to designing your fuzzy loop, and running it on an actual real-time hardware and validation. So thank you very much, and then I'll send it back to Abraham.
Yep. Thank you so much for showing that, Dr. Marsman. So Mehek, why don't you take over now and show us, okay, this was all, this was all very cool. Where exactly can this be used? Where have we used it? What exactly can we do with this in real life?
Thank you, Abraham, and thank you everyone for joining. Okay, so for past few years, we've been working with some academic institutions and some other companies to validate and test these controllers. And we were able to secure government funding to do that. So we do have partners in India as well. Plus, we're working here in Canada as well. So now, in terms of applications, the fuzzy logic control can be used in wide application, in wide applications with home appliances being one, automotive industry, robot control. You can use it in boats and ship, environmental control equipment, air filters, medical filters, etc. Power electronic applications. Specifically, our partner Serpo Consulting is gearing towards using these controllers in home appliances and electric vehicle market in India. And we can, one other application that we can use, and especially with our multivariable interactive capability, is to use it in applications like drones for package delivery or human transportation as well, to achieve certain stability. That would really be the prime of where we will use this technology. So in terms of what we've tested so far, and we overcame quite a few challenges during these tests. I just have a summary to share with you, and then I want to go by sector and industries in where we think we can bring benefit. So our technology is basically like an enabler for other technologies to achieve their efficiency goals. And we can, when we did it in battery chargers, for example, it was very non-linear and also complicated system with battery stacks of different sizes, a very dynamic environment within the battery. And as Dr. Janabi mentioned, that even the model that we created for this battery charger was complicated. But we realized some really interesting benefits from that test. We were able to charge the battery 42% faster than the standard battery. And there were energy savings of approximately 15% that we estimated were realized. And also when we were using the battery, it lasted 125% longer because of the faster charging. Plus we were able to go all the way up to 100% charge, as opposed to the 80% charge that normal batteries have as a safety because of the temperature control issue within the batteries. Then we also used it in a motor control application. Compared to PID, it was 146% faster settling time when we had disturbances. At temperature control, there's PID, and there's companies that are trying to use fuzzy logic or have used fuzzy logic in temperature control because it's a slow acting control loop. This was our first project, and we saved over 31% of energies in that scenario. Now, for our fourth task that we did, which is the process industry, I'll just tell you a bit of a story. When I first met Dr. Janabi and I was learning about AI and fuzzy logic, I didn't know anything about the subject, but we had many sessions when he was teaching me about how it works and what the Autotuner is. And there came a point when I said to him, so basically this Autotuner would work better when the complexity of the system, when the system becomes more complicated. And I clearly remember when the look he had on his face, he was quiet and he was silent. I didn't know what to make of it. And then he started laughing. So I knew the answer was yes. And when we tested this in this distillation column application, the first test we did was a 2x2 system. And in 2x2 system, the settling time was faster about, for disturbances, I think it was about 52% or so. But then when we went to the 3x3, it was 87% faster compared to the PID. So as the applications, you can see, are getting more complicated, from temperature control to fast acting motor control or the battery chargers, even the distillation with multivariable interactive system, we are realizing better control and more benefits. So now I will go through some industrial benefits that we believe this can bring into the industry. So now if we look at the oil and gas industry, some of the challenges that we have is, is environmental hazards and also energy consumption. Okay. So that's the challenge. And as we know, with our climate change agenda of Canada, we are targeting certain industries. And these are the challenges we're trying to overcome. What we can offer there is that our Autotuner can be used in process control with multivariable interactive systems to realize energy savings is a given. Plus, we have optimal fuel usage. So from the get-go, right from the beginning, you are preventing greenhouse emissions from happening. There are a lot of technologies out there that are, carbon capture and such that are trying to do remedy type of controls for, the impact it has on the environment. But if we have a very optimized system, especially when we have multivariable interactive systems, right from the get-go, we are giving environment the benefit of not releasing the greenhouses. And obviously, we'll have, for the main process, we raw material savings. Because of the reduction of byproducts, we realize other benefits like reduced requirement for chemical waste treatment, release of hazardous materials to environment, and also reduced air pollution. So one of the applications that we are talking to people about, and people want to see more, are controllers to be used in are pumps and compressors in this oil and gas industries because of the variability in fluid and our ability for our controllers ability to adapt to disturbances. So this will provide smoother equipment operation for pumps, compressors, and of course other equipment as well. So next we have the electric vehicle industry, where is again the battery management system. Battery in itself is a complicated system, but once you put it in a car, you have other complications happening. Like temperature control and such. So energy saving, yes, and then we have faster charging. When we did this, it was a reliable. One of the comments that we got from Lambton College and the Green Centre Canada, who we did the project with, that they found it to be a safer. Our edeX to be a safer option to use than other systems. And it was also reliable. And throughout the testing, the temperature, we didn't have any overshoots of the temperature, and the temperature control was optimal. We extended the life of the battery, which could also, we can realize the benefit of not generating hazardous waste. And another application, again, which is is a big demand in India because of the hot weather there, is to combine the temperature, to balance the temperature cooling of the battery with cabin cooling and also battery cooling, which we could also explore. And this is just like I'm talking about the battery, but obviously a controller of this type can be used in many applications within electric vehicle, and there are motor control benefits as well. These examples that I've picked are based on some of the testing that we've done already, but of course we can do more than this. So now in HVAC and heating and cooling industry systems, when we're talking about buildings, for example, or plants and factories, there are a lot of disturbances that the HVAC system would have to adapt to, and our solution, as we've seen in our testing, is that we have a very fast response to disturbances. Again, energy savings given, then we have some causes of disturbances, what can, like process variations, environmental changes, or human traffic within the buildings. Since we can not just do temperature control, but we can also do motor control. We can combine multiple control loops within air conditioning and heating systems to realize more benefits. Okay, so I'm just going to fast track from some of these. Basically, what this is for is that we can do retrofit and work with existing system instead of getting more systems. There's a question I think that we want to take. So
and there's a number of questions. There's a number of questions.
So we'll stop here for timing and take the questions. So Abraham, you want to ask the question?
Yeah, sure. Dr. Janabi, are you there? Perhaps why don't you continue and okay,
Yeah,
there we are.
sure,
Okay.
sure,
Yeah, so we had a number of questions. One of them is by Rod McKay. He says, if you had a system with several control loops, each of which may present a disturbance to the others, would the fuzzy logic controller be able to tune all of them as a whole? The specific example here is an extruder with several barrels bolted together, with each barrel treated as a heat zone with its own TC and PID controller. Could the fuzzy logic controller treat the combined zones as one system?
The answer to that is yes, because that is what we call multivariable interactive system.
Sorry, just a clarification. He put a note here. The barrels may have different set points.
That's okay, of course.
Okay, yeah, go ahead.
In process industry, every variable has its own set point. So if you're talking about temperatures, pressures, and so on and so forth, they are different, but they all affect each other. For example, flow affects pressure and pressure affects flow directly. Anyway, but their set points are different. So yes, the answer to that is yes. And this is what the example that Mehek has just shown of the 3x3 system. That system had interactive behavior where every disturbance on any of the loop affected all the loops.
Okay, and someone else, sorry, go ahead, finish.
Yeah, when we talk about multivariable interactive systems, there are two stages that can be, of course, combined to one stage. One of them is to reduce the interaction, and the other is to get the loops behave the way that we would like them to behave.
Okay, and someone else, Hadi Sharifi asks, are you planning to test fuzzy logic controllers on processes that go through frequent transitions? For example, various grades of polyethylene manufacturing.
We would like to do that. We'd like to work with companies who have a problem like this to work with. Absolutely, we'd like to use our controller everywhere we can.
And Arun asks, have you tried using your auto-tuning? Have you tried auto-tuning a fuzzy controller to tune PID and anti-wind-up constants?
Well, here is the point. I guess this question comes from the fact that a lot of people are saying that they have fuzzy controllers, and when you look at them, they either have two controllers working together. One of them is fuzzy, and the other one is PID, where the fuzzy works first, then the PID takes over, etc. And I don't want to go into the technicality of it. And others, they use a fuzzy controller to actually tune the PID. We do not need to use a fuzzy controller to tune the PID. Our tuner is capable of tuning the PID. And if somebody is interested in the PID, yes, we can tune the PID. We have our own sophisticated PID that we can offer as well. Have we tested that? The answer is no, because we would like to do that, and I don't think we will have a problem to do that. In fact, it's not a very complicated problem. We are trying to promote fuzzy logic control because we believe it's superior, but we can still use we can use PID as well.
By the way, guys, if you feel your question has been answered adequately, do let us know. If you have any follow-ups or you feel like we didn't exactly get what you're aiming for, do feel free to follow up and we will try to answer. Charles Chatier asks, how comparative is the Autotuner with model predictive control software on a price basis? Is it possible to replace prohibitively expensive model predictive control software with the fuzzy logic Autotuner?
Yeah, the answer is yes.
Well, he said how comparative. So I don't. Well, I guess the first part of that, if you can. Uh, he said how comparative is the Autotuner with model predictive control software on a price basis?
Yeah, to be honest with you, I do not know how much the price of the predictive control auto tuning, but my understanding is that it's a big software. Our tuner is highly intelligent, but it's not a very big software, and so it will be much cheaper than predictive control. Definitely, I do not have prices to compare, but it will be cheaper.
Hadi Sharifi asks how fuzzy logic controller interacts, if possible, with AI in predicting future air pollution on past historical data.
Can you repeat the question?
Yeah, so he's asking how the fuzzy logic controller would would interact with AI in predicting future air pollution based on past historical data.
Okay. Fuzzy logic can be used either the predictor itself, or it can be used the decision maker to explain what the prediction will be. I'm not sure what the exact problem is, but because to talk technical, we need to know the details of the technicality of the problem. But can they work together? Yes. In what capacity? Either in prediction capacity in conjunction with the AI, whatever that means. Like which part of AI will it be? Is it machine learning? Is it rule generation? And the other is the decision making. Okay, now is our prediction correct? Is it exact? Is it precise? So fuzzy logic can give us an area of comfort zone.
And the Autotuner can enable us to get our answers faster than some of the other technologies we're seeing in artificial intelligence with learning systems. Learning systems, definitely we'll work with them. But right, Dr. Janapi, if you...
Yes, we can work with other technologies side by side. We can amalgamate our technology to other technologies to work in synergy together. Absolutely. We have the power of tuning other variables, not just the fuzzy logic controller. Our tuner is capable of modeling. It's capable of what we just showed. It's doing modeling. It's capable of tuning an intelligent system, would be it fuzzy controller or non-fuzzy. It is capable of tuning and optimizing PID performance. It is capable. Let's say a user has his or her own design of fuzzy controller. Can we optimize that controller for a given application? And the answer is yes. Even if it's not our controller, we can still optimize it. Of course, we need a bit of work to accommodate that controller, but yes, we can do that. And actually, for that matter, we can optimize any type of control, like the model predictive control. We can optimize that as well without having the expensive software.
Okay, everyone. And with that, I believe we have reached the end time of our webinar. We'd like to thank everyone for coming out. If there were any further questions that you had that that occurred to you or that we didn't get to, please feel free to send out an email, and we will try our best to get back to you. So with that, I guess we will end the webinar. Thank you so much, everyone, for coming. There are 2 more questions. We will stick around to answer these questions. If other people want to leave, feel free to. But Dr. Janabi, there's another question here by Hadi Sharifi. He says, can FLCs interface, or have they been tested with air dispersion models, steady state and unsteady state, such as AirMod, CalPuff, etc.?
Actually, the direct answer to that is we have not. I do not know whether other people have not done that. using manual tuning. We would like to try that. We'd like a company to come forward to say, we have this problem, we would like to test it. But we haven't done that, but we are quite confident that we can do that successfully.
Okay, and someone else asks here, what are the next steps in your platform's growth? I'm a master's student looking to get involved. Oh, that's by Arun. That's by Arun.
Yes, yes, we would like to hopefully as we take our next step to marketing and to further development, we would very much like to have people to get involved with us on the level of R&D. We have quite few things on the plan. For example, version 2 and version 3 of our tuner. We have, and I don't want to go on about that, but we have quite few others. We have large scale modeling, we have intelligent modeling, all kinds of things.
Yeah, so Arun, feel free to send us an email.
Do you, Abraham, do you want to bring up the slide with our email so people can write it down if they?
Yeah, sure. Let me do that. 1 second. So our emails can be found here. Hadi Sharifi says the government of Ontario might be interested. So that's good to hear.
Very good to hear.
Yeah.
We'll give you a call.
Okay, so these are our emails. Feel free to email any one of us if you so please, and we'll give you guys that a minute. And yeah, thank you for coming out, everyone. Please let us know if you benefited. Any feedback would be appreciated. We really appreciate everybody else or everybody coming out.
I think there is a question about LinkedIn. Did you get that, Abraham?
No, I didn't. Was that in the chat? I don't.
Work too? Does LinkedIn work?
Oh, does LinkedIn work too? Yes, it does.
Yes.
Yeah, sure. Go ahead.
Okay.
Yes, you can find this many ways. Well, thank you everyone for accepting our invite and joining us and giving us your precious time. Everyone is very busy, and we hope to continue this, relationship and also dialogue to, test our controller in more applications. All right. Thank you.
Thank you.
Okay. Thanks, everyone.
Thank you, everyone. Yeah.
Okay.
Have a good day.